Exploration plays a key role in human creativity and especially in artistic painting. Art is not about understanding and mastery, it's about doing things and experience, as art critic Jerry Saltz says. In this paper, we focus on interactively controlling geometric shape abstraction and texture in artistic images. Our method allows changing the texture style of an input image using text prompts. Furthermore, the granularity of geometric shapes can be chosen. Also, the texture style can be varied by exemplar images and painterly attributes such as the oiliness. The previously shown image abstraction and texture edits were made possible by using a representation that splits up the style into multiple components. We obtain these components using a process called texture decomposition, for which we now present our proposed technique. Specifically, we aim to separate an image into its coarse, abstracted components and its fine granular textural details. To this end, we propose a two-stage pipeline consisting of a segmentation stage, S, and a pipeline of differentiable image filters to represent the image details. The first stage renders an abstracted variant of the input, for example using a segmentation method such as slick. The second stage represents the image details lost in the first stage. Here so-called parameter masks control specific artistic control variables, for example contours, local contrast, and others. To obtain these parameter masks, the output of the filter pipeline is optimized to resemble the input and the gradient of the loss if backpropagated to the masks. This optimization allows us to split up the style details into its constituent parts. For example, a parameter mask could contain the strength of edges at every pixel. After optimization, the decomposed representation can be further edited by a user. During the structural abstraction stage, the aim is to create an image representation that is easily editable by creating patches of uniform color that represent the coarse features of the image. In principle, any off-the-shelf segmentation or geometric abstraction method can be used. We use slick segmentation, which creates segments of similar size and is especially well suited for downstream editing. Aside from editing, the structural abstraction can also be used for artistic purposes, for example to impose a coarse brushstroke geometry into the image. For this, we employ neural painters that redraw the image using a set of shape primitives such as rectangles. The feed-forward paint transformer network is one such method, which we use for fast artistic geometric abstraction. In the second stage, a differentiable filter pipeline is employed. The concept of differentiable stylization pipelines was recently introduced as so-called whitebox filter learning. It has shown good results in representing example-based styles, such as neural style transfer, by optimizing the parameters of stylization filters. To this end, they implemented several effects such as oil paint or watercolor in a differentiable manner in PyTorch and then optimized the effect parameters as previously discussed. In our approach, we make use of this concept, however we introduce a new pipeline specifically for reconstructing only the details lost in structural abstraction. This allows us to keep the number of necessary filters low, which greatly increases speed and ease of editing. Specifically, our pipeline consists of a bilateral filter for edge-aware abstraction, an extended difference of Gaussian, or XDOG, for adding edges and contours, a painterly rendering filter for which in our case we use a bump mapping filter that is especially well suited for oil paintings, and finally a contrast enhancement filter. Each of these filters can be controlled by one or more parameters, and each parameter can be adjusted on a per pixel level using the previously mentioned parameter masks. Our ablation experiments show that every filter is necessary for being able to represent a wide range of texture details. For example, if we remove the bilateral filter, details of the clock face on the right are lost and similarly contours are not present in full strength without the XDOG. Next to the L1 loss for texture decomposition, other losses can also be used to optimize the parameter masks to achieve artistic stylization effects. For instance, we show the use of neural style transfer losses and implement two popular style losses which can be optimized given a style exemplar image. Here an image has been stylized using a marble ink style image. We also implement a clip-based loss for text prompt-based optimization of parameter masks. The loss network is the clip network that translates text and images into the same representational space. We employ a patch-based loss as proposed by ClipStyler. In this example, an input image has been stylized using the text prompt fire. While optimization can in many cases recover the input image almost perfectly, it is slow to optimize, taking around 20 seconds up to a minute. To speed up this process, we train a feed-forward parameter prediction network, also called PPN, which directly predicts the parameter masks used in the filter pipeline. The trained PPN can then be used for real-time parameter reprediction during image editing. We use neural style losses to train the network on a single style. During training, these losses are backpropagated as gradients through the filters and parameter masks to the network. While the first stage is not differentiable, it must still be included as a pre-processing step to create abstracted inputs for the second stage, i.e. the arbitrary style pipeline, which we train the parameter prediction network for. The full training stylizes an image using the fast NST of Johnson et al., and then abstracts the image using the first pipeline stage, passing the output to the parameter prediction network and the effect pipeline. The single-style PPN results closely resemble the inputs of the Johnson NST it was trained on. In some cases, certain details can be wrongly predicted, such as the eye's pupil on the right. We also train arbitrary style transfer PPNs. These are networks which mimic arbitrary style transfer networks, such as the style attentional network, or SANet, i.e. a single network that can handle any arbitrary style it is given during inference. We now show a few editing examples. During editing, we can modify values of the parameter mask. For example, here, we increase the oil bumpiness and shininess in the background. In this image, we modify colors in the structural abstraction stage to move yellow stars from the building to the sky, and then repredict fine textural details with the PPN. In this example, we remove structure of the mosaic style from the face. This is done by selecting the face segments and merging them to a uniform color and then repredicting the style using the PPN. We now show interactions with our tool for stylization control and editing. Our example shows a style transferred image in which we want to vary the geometric abstraction and texture style. In the segmentation stage, we can adjust the number of slick segments. However, as we would like a more abstract shape primitive, we switch to the paint transformer. This stroke-based method offers the choice between multiple geometric primitives such as rectangles or circles, and the granularity represented by the stroke layers can be adjusted. We now want to make the texture adjust to the underlying geometric shape abstraction while at the same time adhering to a particular style. In this case, we use a text prompt to define our new target texture style, which is then optimized using clip-based losses. Optimization takes around 20 seconds on a modern GPU. In this example, we want to blend together two styles. The first style is optimized with the text prompt fire. The optimization produces a set of parameter masks, which can be interpolated. In our editing workflow, the parameter set is saved as a preset, and then a second style is optimized, this time using the text prompt star. We can now interpolate the parameter sets, for example based on the depth or saliency prediction. In this case, we choose depth and an interpolation factor. The fire style is now retained in the face, while regions which are predicted to be farther away are stylized in the star style. The blending between both regions is seamless as parameters are interpolated smoothly. In our next example, we want to aesthetically enhance an image using local editing. For this, we can edit the parameter masks after decomposing the image's texture. We choose the appropriate parameter to edit, such as amount of contours, and then draw on the canvas to increase or decrease values in the selected region. The color mapping on the left displays the strength of parameters per pixel, while the editing result is shown on the right. Here, we increase the contour amount in the eye and mouth region. We then again save these parameter masks as a preset and then want to optimize the texture to a new style. However, this time, instead of text prompt, we use an exemplar image with a marble texture pattern and optimize our parameters using the statistics-based style transfer loss. After optimization, we blend together the current parameters and the previously saved parameters based on predicted depth values. Finally, we apply global edits, as we want to increase the oiliness of the image. For this, we increase both the scale of bumps as well as their specularity. In our final example, we show editing using segments for correcting artifacts in neural style transfer images. We wish to remove the red dots on the forehead created by a feed-forward style transfer network trained on the candy style. We thus select these segments and then select a region from which we want to transfer the color. The middle pane shows the output after the segmentation stage, while the right shows the effect output. To show the result of edits in real time, we have trained a parameter prediction network, in this case on the same style as the style transfer network which created the input image. As we change the colors of segments using color transfer, the parameter prediction adapts the local output style in the edited region to the rest of the image. This allows for easy editing of style transfers while keeping the global style and content structures intact.